Hi. Someone saluted, that's good. Okay, so who is currently, like, you're at school? Okay, like, you're not during the holiday. Who's not on holiday? Okay. And who is on holiday? Ah, okay. Cool. Yeah, so what should we start with today? Do you guys remember Cheva's theorem from last time? Sort of? Yes? Yes, sort of. Okay. Anyway, I'll introduce it to you again. So basically today we're going to be doing different triangle centers and why they are triangle centers and some other interesting stuff about it. Cool, Jazz? Sound good? Good. Okay. So, Cheva's theorem is a theorem about when you have three, that is a straight line. It's a theorem about when you have three Cevians concurrent. Now, do we know what a Cevian is? I'm guessing not, but just, does anyone know? Good, okay. So a Cevian, when you have a triangle ABC, a Cevian is just a line which goes from one of the points, or any line which goes through one of the points of the triangle. So let's call this D, E, F. So CF is a Cevian. Cevian. Hello. Welcome. Okay. So I'm sure if you imagine in your head, you've got a triangle, you've got three lines, AD, BE, CF, and these lines are moving around. It should be something special when these three lines actually go through the same point. And Cheva's theorem helps you to either prove that these lines do go through the same point when they do, or gives you some kind of criteria you can work with. So, Cheva's theorem says the following, that, so given that diagram, AD, BE, and CF are concurrent if and only if this following equation holds. So AF over FB times BD over DC times CE over EA is what? Okay, so maybe you want to take some time to digest that, maybe not.
Yeah. Does Ceva's theorem also hold if E is on AAC extended, for example?
Yes, but then you have to use directed. Oh, actually, yeah, you don't need to use directed sides. Yeah, it does still hold.
Okay, thank you.
So it does hold if that point there is outside the triangle. So like that, in that case, it would look something like there. Okay, that's a bad example. Okay. So let's say the point is there. You could have these three lines. That's a point. And then if that's A, you just have to look at where this line intersects the opposite side. And then that would be D. Okay, everyone got that? How it works when it's outside the triangle? Most of the time you'll be dealing with cases where it's inside, but it's good to know how the outside case works as well. Okay, so maybe it does for you, but for me, I would never be able to remember an equation like that. For me, I would rather kind of have the picture in my head and say which segment divided by which segment times so on. So you can basically start at any vertex, at C, and you go around and you say, okay, that length divided by that length times that length divided by that one times that one divided by that one. And that has to be 1. Cool. So okay, let's just show you how this would be used. So I'll show you how it's used and then we can do a proof of it, which is actually not too hard. Okay, so special case. Let's suppose that D, E, and F are midpoints. So each of those points on the sides of the triangle are actually midpoints of the triangle, of the respective sides. Cool. And then, okay, then what is this fraction? AF over FB, what is that equal to? 1. And the next one is equal to 1, and the other one is also equal to 1. Okay, so in that case, it's easy to see that this equation holds, because 1 times 1 times 1 is equal to 1. So what we then prove in that case is that the lines, the medians. So CVN is any line from one point to the other side, but a median is a line from that point to the center of the opposite side. So the medians intersect, and the point of intersection is called
centroid.
Yes. Cool. So if these are midpoints, then usually they use the name G for it. G is the centroid. Any idea why do we use the letter G? What he said. Okay, so it's the center of gravity, which means what?
If you hold it at that point, the triangle balance.
Okay, cool. That is, yeah, pretty much what he said. Okay, so G is the centroid if those are midpoints. So that's one way that you can prove that the medians intersect. I'm sure you might have seen other ways to do it as well, but this is one way to do it. Okay, now shall we prove Chever's theorem? Yes, yes, I think I got one yes. Okay, good. Okay, so we're going to look at this ratio, AF over FB. And basically we're going to prove that this fraction is equal to another ratio. And we're going to do the same for each of them, and when we multiply those three results together, we're going to get 1. So, just to be clear, okay, so do you understand what this if and only if means? No. Okay, so what it means, so when you have a theorem that has if and only if, it has one statement before it and one statement after. And what this if and only if means is that if this is true, then this is true. And if this is true, then this is true. So those two statements are linked. So if one of them is true, then the other one has to be true as well. So when you have a theorem or a problem in a paper, and they ask you to prove that something is true if and only if something else is true, you have to do both directions. You have to start with this and prove that, And you also have to start with this and prove that. Cool? That's very important. You have to prove both directions. So what we're going to do, so we're first going to prove this direction. If these are concurrent, then that ratio is 1. Cool? So we're assuming that these three lines go in one point. Let's keep on calling it G. Now, AF over FB is equal to, how do you guys write the area of a triangle? What notation do you use? Teachers, please, how do you write the area of a triangle? I mean, there's different ways of doing it, but I just want to know what your notation is. No, not the formula. How do you, like the word, the area of triangle?
Just A.
So just like AFG, like that.
That's fine.
Okay. G, big friendly giant. Okay. By the way, have you guys read the BFG?
Yes.
Okay, good. You have to, if you haven't read it, you have to read it. Anyway, so, okay, my personal